Two black holes collide. In a fraction of a second, more energy is unleashed than every star in the observable universe has radiated since the Big Bang. No explosion, no light, not even a sound. Just a whisper in the fabric of reality itself, thinner than an atomic nucleus, travelling 1 billion light-years to reach us. For most of human history, these catastrophic events were completely invisible to us, utterly silent. And then, one September morning in 2015, a machine we built in Louisiana heard something it was never supposed to hear. Something that changed physics forever. By 2025, we have heard over 300. And what those signals are quietly whispering back to us about the nature of reality is the part nobody is prepared for. Stay until the end. If you're new here, welcome. Stay until the end. Because nobody told you the part beyond the discovery, the part that makes the last century of physics look like an opening act. The events are real. The mystery is deepening with every new signal. And it started with a vibration thinner than an atom that somehow crossed 1 billion light-years to find us. Now, let us get into it. Part 1. The clearest black hole, merger ever recorded, just broke the model. When two black holes collide, the universe does not bother announcing it. There is no explosion, no flash of light racing across the galaxy to warn anyone. Just a wrinkle in the fabric of space-time itself, travelling outward at the speed of light, stretching and compressing everything it passes through by an amount so small it would take the entire width of a human hair and divide it into 10,000 pieces before you would even be in the right neighbourhood. That is what we are detecting. That is what we built the most precise measuring instruments in human history to find. And in January of 2025, one of those instruments caught something that made physicists stop mid-sentence. The event is catalogued as GW25114. Not the most poetic name, but scientists were clearly too busy being astonished to worry about branding. What arrived at the LIGO and Virgo detectors that day was the clearest, sharpest, most information-rich gravitational wave signal ever recorded in the 10 years since we first started listening. And the strange part, the part that is still being talked about in research groups around the world, is that the signal was almost too perfect. Not perfect in the sense of clean data. Perfect in the sense that it matched the mathematical predictions of general relativity with a precision that borders on unsettling. To understand why that matters, you need to think about what happens at the very end of a black hole merger. Two black holes, each one millions or billions of times the mass of our Sun, have been spiralling toward each other for perhaps billions of years, slowly draining orbital energy away as gravitational waves. When they finally collide, they do not simply merge quietly. The resulting object, one single enormously massive black hole, wobbles. It vibrates. It rings, the way a bell rings after you strike it. Not with sound, but with space-time itself oscillating back toward equilibrium. Physicists call this the ringdown phase, and the specific frequencies it produces are called quasi-normal modes. Here is what makes GW25114 remarkable. The signal was clear enough, the noise low enough, the sensitivity of the detectors high enough, that scientists did not just detect the fundamental mode of that ringdown, the main tone of the bell. They detected the first overtone, a harmonic, a second layer of vibration riding underneath the dominant frequency, exactly the way a real bell produces not one pure note, but a chord of overlapping tones that give it its character. Detecting that overtone required a signal-to-noise ratio that previous events simply could not deliver. Think about what that means for a moment. We're talking about an event that happened so far away, the light travel time dwarfs anything our minds can comfortably hold. The ripple that arrived at our detectors in 2025 had been travelling through the universe for an enormous stretch of time, diluted across billions of light-years of expanding space, and it still arrived carrying enough information to reveal the secondary harmonics of a newly formed black hole's vibration. That is the equivalent of pressing your ear to the ground in Nairobi and hearing a specific chord played by a single guitar in Tokyo. The reason scientists care so much about those harmonics is a field called black hole spectroscopy. The concept is elegant, almost musical in its logic. General relativity, specifically the version describing rotating black holes called the Kerr solution, makes a very firm prediction. The ringdown frequencies of any black hole are determined entirely by two numbers, its mass and its spin, nothing else. Not what it ate, not what it was made from, not what happened to the matter that fell in, just mass and spin. If you know those two numbers, you can calculate every mode, every overtone, every harmonic the black hole should produce. This is called the no-hair theorem, the idea that black holes carry no distinguishing features beyond those two quantities and their electric charge. GW 25114 gave us enough data to actually test this, to take the measured fundamental mode, use it to infer mass and spin, and then check whether the overtone matches what those numbers predict. And it did. Almost perfectly. Which should feel like a victory, and in many ways it is. But there is a tension building inside the physics community around exactly this kind of result, and it is a tension worth sitting with. The fourth observing run of LIGO, Virgo and Kagra, the collaborative network of gravitational wave detectors spanning the United States, Italy and Japan, produced something in the range of 120 new candidate events, on top of the roughly 200 already catalogued from previous runs. The detectors themselves were operating at sensitivities that would have seemed like science fiction even a decade ago. Quantum squeezing techniques, upgrades to mirror coatings, improvements in seismic isolation systems, all of it combining to push the detectors closer to their fundamental physical limits. The result is that the signals arriving from these mergers now carry more information than ever before, and that information is doing something philosophically uncomfortable. It is confirming the theory almost without exception. And here is the tension. When you have a theory as powerful as general relativity, and you build instruments capable of testing it at extreme precision, and the theory just keeps passing every test, there are two ways to feel about that. The first is satisfaction. Einstein was right. The universe follows rules, and we are clever enough to verify them. The second is a creeping suspicion that either nature is hiding something in the places we cannot yet see, or that our instruments are so perfectly tuned to what general relativity predicts that we might be inadvertently filtering out deviations before we even notice them. Some physicists are asking whether the Kerr black hole, the mathematical object, the perfectly smooth, perfectly symmetric rotating singularity described by the equations, is just a little too perfect. Nature tends not to produce textbook examples. The cosmic microwave background has anomalies. Galaxies do not distribute themselves exactly as simulations predict. Dark matter, dark energy, the Hubble tension, all of these represent places where the universe refuses to colour inside the lines. So why are black holes behaving so obediently? There are speculative answers. String theory predicts that black holes should not be the smooth Kerr objects general relativity describes. Instead, they might be what theorists call fuzzballs, objects where quantum effects smear the would-be singularity into a tangled knot of string at the Planck scale, and where the event horizon, rather than being a clean mathematical surface, is a region of chaotic quantum activity. Other frameworks predict firewalls, or quantum hair, or subtle imprints in the gravitational wave signal that encode information about the interior. None of these have been detected. Every ringdown, including GW 25114, says Kerr, perfect, smooth, boring in the most astonishing possible way. But here is where your curiosity should stay switched on. The fact that we have not detected deviations does not mean deviations do not exist. It means our instruments are not yet sensitive enough to find them if they are small. The first overtone detection from GW 25114 represents a new frontier of precision, and theorists are already calculating exactly what kinds of quantum gravity effects would produce signatures at the level of sensitivity we now have, or just below it. The next generation of detectors might find something that changes the picture entirely, For now, though, we are left with a universe producing some of the most extreme events physically possible, and those events are arriving at our instruments bearing signals that say, with increasing clarity, the math works, the geometry is correct, the black holes are real, and they are exactly what the equations predicted. That perfection, as we're about to see, becomes its own kind of mystery when you zoom out and look at not just one event, but 300 of them. Part 2, the 300 plus event problem. We are no longer in the discovery phase. On September 14th, 2015, at 5:51 in the morning Eastern Time, a ripple in spacetime arrived at the LIGO detector in Livingston, Louisiana. 7 milliseconds later, the same ripple arrived at the sister detector in Hanford, Washington. The signal lasted roughly 0.2 of a second. It had travelled approximately 1.3 billion light-years to reach us. It was the first direct detection of a gravitational wave in human history, and it confirmed the merger of two black holes that together weighed about 65 times the mass of our Sun. Scientists called it GW 15914, and when the discovery was announced publicly in February of 2016, it felt like the universe had finally consented to be heard. That was one event, one signal, one confirmation that the instruments worked, that the theory was right, that black holes merge and that the resulting ripples are real and measurable. What has happened in the decades since is a transformation so complete that it is difficult to fully appreciate without stepping back and looking at the shape of it. By the end of the third observing run in 2021, the catalogue contained roughly 90 confirmed events. By the time the fourth observing run pushed into 2024 and 2025, that number had climbed past 300. 300 gravitational-wave events. 300 separate instances of black holes, or neutron stars, or combinations of both, colliding somewhere in the universe and sending their announcement rippling outward across space-time, and us, on this small planet, catching it. Gravitational wave astronomy is no longer in the discovery phase. It is in the data analysis phase, the interpretation phase, the phase where the sheer volume of detection starts to reveal patterns, and where those patterns are raising questions that no single event ever could. Here is the shift that matters. When you have one detection, you can say, "We found one." When you have 300, you have a population. You can ask statistical questions. What is the distribution of masses? What is the distribution of spins? How do mergers cluster in the universe? Are the properties of these systems random, or are there preferred values, preferred ranges, preferred combinations? And when you start asking those questions, the data begins to look structured in ways that nobody fully expected. The mass distribution of merging black holes, for instance, is not smooth. If you plot the masses of the black holes detected so far and look at how they are distributed, you do not get a featureless curve. You get clustering. There appear to be pile-ups at certain mass ranges and relative scarcity at others. One feature that stands out is an apparent excess of black holes around 35 solar masses. Another is the mass gap we will return to in more detail shortly. But even setting aside the specific features, the very existence of structure in the mass distribution tells you that something physical is producing it, some process or set of processes that preferentially creates black holes of certain sizes and less commonly creates others. The spin distribution is, if anything, even more interesting and more contested. The spin of a black hole, how fast it is rotating, carries information about how it formed and what happened before the merger. Black holes formed from the collapse of a single massive star are expected to have spins that are somewhat aligned with the orbital plane of the binary system, because the angular momentum of the progenitor star tends to be inherited by the black hole. Black holes that ended up in a binary through dynamical capture, meaning they were originally separate objects that fell into each other's gravitational influence through interactions in a dense stellar environment, are expected to have spins that are randomly oriented relative to the orbit. This is because the pairing happened independently of each individual object's rotation history. When you look at the spin distribution across 300 events, you find both kinds. You find systems that look like they form together from binary star systems evolving in isolation, and you find systems with misaligned spins, high spins, exotic spin configurations that point toward more chaotic formation histories. The question is, what fraction of mergers came from which channel? And the answer, frustratingly, is that we do not yet know with confidence, because teasing apart the two populations requires more events and better measurements than we currently have. This is where something subtle but important enters the picture. The events we detect are not a random sample of all the mergers happening in the universe. They are a biased sample. The detectors are more sensitive to certain kinds of mergers than others. Heavier systems produce louder signals and can be detected from farther away. Face-on mergers, where the orbital plane points roughly toward Earth, produce stronger signals than edge-on ones. Systems with certain spin configurations produce slightly different waveforms that affect how easily the matched filter pipelines identify them. In other words, the 300 events we've recorded are the 300 that were loudest and most detectable, not necessarily the 300 most representative of what is actually out there. This creates a real methodological challenge. When you see a clustering in the mass distribution, how much of that is a genuine astrophysical feature, a real preference in how the universe builds black hole binaries, and how much of it is an artifact of what the detectors are able to see? The field has developed sophisticated tools for correcting these selection effects, but the corrections rely on models of detector sensitivity that are themselves imperfect. You're essentially trying to reconstruct a three-dimensional object from its shadows, and the shadows are not perfectly sharp. Think of it this way. Imagine you are trying to understand the size distribution of fish in a lake, but your net has holes of a certain size, so anything smaller than 6 inches slips through. If you pull your net and find that most of the fish you catch are between 8 and 12 inches, you cannot conclude that the lake mostly contains 8 to 12-inch fish. You have to account for the fact that the small ones are invisible to you. Gravitational-wave astronomy has the same problem, except the net is made of quantum noise and seismic interference, and the fish are merging black holes billions of light-years away. None of this means the data is wrong, or that the patterns are illusions. It means they need to be interpreted carefully, and it means that as detectors improve and the catalogue grows, some of the features we currently see in the distribution may sharpen into cleaner astrophysical signals, while others may soften or disappear as we realize they were artifacts of our detection sensitivity. The universe is telling us something through these 300 events. We are still learning how to listen without projecting our own limitations onto what we hear. And speaking of things the data seems to be telling us that we are not entirely sure how to explain, there is the matter of a particular region in the mass distribution, where black holes are not supposed to exist at all, except that several of them apparently do. Part 3. The mass gap is starting to look artificial. There is a region in the black hole mass distribution where stellar physics says nothing should live. It runs from roughly 65 to about 120 times the mass of our Sun, and it is called the pair instability mass gap. The name comes from the physical process that is supposed to create it, and the physics is genuinely dramatic in its own right. When a massive star reaches the end of its life, its core collapses under gravity. The outcome depends heavily on how massive the core is. For stars in a certain mass range, the collapse produces a neutron star. For heavier stars, it produces a black hole. But there is a range corresponding to progenitor stars of roughly 130 to perhaps 250 solar masses depending on the metallicity of the star, where something different happens before collapse can occur. The core becomes so hot that gamma rays in the interior begin spontaneously converting into electron-positron pairs. This is quantum electrodynamics doing something deeply counterintuitive, where light, photons, produce matter and antimatter out of nothing except energy. The problem for the star is that this process removes radiation pressure that was holding the core up. With less outward pressure, the core contracts suddenly, triggering a runaway thermonuclear explosion that does not just end the star's life, it completely obliterates it. No remnant, no black hole, just an expanding cloud of stellar material that rejoins the interstellar medium. The prediction, then, is straightforward. Stars massive enough to undergo this pair instability supernova leave no black hole behind. Stars just below the threshold leave black holes topping out around 60 to 65 solar masses. Stars far above the threshold, if they even exist in meaningful numbers, might collapse directly to black holes above 120 solar masses without going through the instability. The gap in between, 65 to 120 solar masses, should be empty. And then we detected GW 19521. The event involves component black holes of roughly 85 and 66 solar masses respectively, producing a merger remnant of roughly 142 solar masses. At least one of those components sits squarely inside the pair instability gap. The black hole of 85 solar masses should not exist, according to the standard stellar evolution picture. It is a forbidden object appearing in our data like an uninvited guest at a party where the venue had been specifically reserved for someone else. Then in 2023 and 2024, more events with component masses in or near the gap appeared in the catalogue. The forbidden zone is beginning to look less like a void and more like an underutilized neighborhood. The mainstream explanation is hierarchical mergers. The idea goes like this. In dense stellar environments, globular clusters, nuclear star clusters, the regions close to the centers of galaxies, black holes do not live in isolation. They interact gravitationally, swap partners, form new binaries, and sometimes merge with each other. A black hole that results from a merger of two smaller black holes is called a second-generation black hole. Its mass is approximately the sum of its parents' masses, minus whatever was radiated away as gravitational waves during that first merger, which is typically around 5%. A second-generation black hole formed from 235 solar mass parents might weigh around 66 or 67 solar masses, right at the edge of the gap. If that object then finds a new partner and merges again, the result could easily push into the forbidden zone. This is an elegant solution, and the spin distribution provides some supporting evidence. When two black holes merge, the resulting object's spin is set by the angular momentum budget of the collision, and for a wide range of mass ratios and initial spin configurations, the outcome tends to cluster around a spin parameter of about 0.7. This is a theoretical prediction, and it is roughly consistent with what we see in the population of events suspected to involve second-generation black holes. The universe seems to be building black holes in factories, dense clusters where gravity acts as both matchmaker and forge, repeatedly melting and recombining objects until they grow beyond what any single stellar death could produce. But there is a competing explanation that the data cannot yet rule out, and it involves a different kind of black hole entirely. Primordial black holes are hypothetical objects formed not from stellar collapse, but from density fluctuations in the very early universe, in the first second or fraction of a second after the Big Bang. In regions where the universe happened to be slightly denser than average, gravity could have overcome the outward pressure of radiation and caused a collapse, forming a black hole before any star had ever formed, before any element heavier than hydrogen and helium existed in meaningful quantities. These primordial black holes would have no stellar progenitor. They would have no reason to avoid the pair instability mass gap, because that gap is a consequence of stellar physics, and they were never stars. They could, in principle, exist at any mass. The frustrating thing is that at the level of data we currently have, a population of primordial black holes contributing to some fraction of the detected mergers looks similar to a population of hierarchically assembled second-generation black holes. Both could produce mass gap events. Both could produce certain spin distributions. Distinguishing between them requires either more precise measurements of individual events, or enough events at enough different mass ranges to statistically separate the two populations. What the mass gap really tells us, at this point in our understanding, is that black hole formation is not a single process producing a single kind of object. The universe is apparently building black holes through multiple channels, with different histories, different environments, different mass scales, and the gravitational waves they produce carry the fingerprints of those histories if we can learn to read them clearly enough. The possibility that some fraction of the black holes we're detecting were not born from stars, but from the universe's own early turbulence, carries a philosophical weight that is hard to overstate. It would mean that some of the objects we're detecting have been in existence since before the first stars formed, since before the first galaxies assembled, since before the universe had cooled enough to allow chemistry. They would be the oldest individual objects in the cosmos, relics of the first instant of structured space-time. That thought alone should make you want to listen more carefully to what the signals are saying. Part 4. The ringdown revolution. Black holes are too perfect. Every black hole merger has 3 chapters. The inspiral is the long, slow opening act. The two objects spiraling toward each other over timescales that can stretch to billions of years, radiating gravitational waves that carry away orbital energy and bring them ever closer. The merger is the main event, brief and catastrophic, lasting milliseconds for stellar mass black holes, longer for more massive systems. And the ringdown is the closing chapter, the period immediately after the collision, when the newly formed single black hole shakes and wobbles its way back to the smooth, stable configuration that general relativity demands. It is the ringdown that physicists find most interesting right now, and the reason goes back to something fundamental about how general relativity works. The Kerr solution, the mathematical description of a rotating black hole, is one of the most elegant exact solutions in all of physics. It describes the geometry of space-time around a rotating mass with complete precision, and it makes an extraordinary claim: the space-time around any black hole, regardless of what created it, regardless of the details of the matter that collapsed to form it, is completely described by just 2 numbers, mass and spin. Every feature of the geometry, every geodesic, every orbital frequency, every quasi-normal mode of the ringdown, all of it follows deterministically from those 2 values. The no-hair theorem, which is the formal statement of this, is one of the most tested and most philosophically striking predictions in all of physics. It says that black holes have no memory. They do not remember whether they formed from a star of iron or a star of carbon. They do not remember the magnetic field of their progenitor, or the turbulence of their final collapse, or the history of everything that ever fell into them. All of that information, in the classical general relativistic picture, is irretrievably lost. What remains is a smooth, featureless object defined entirely by mass and spin. GW 25114, with its overtone detection, gave us the sharpest test of this prediction yet. The fundamental quasi-normal mode was measured, the overtone was measured. The 2 together constrain the mass and spin of the final black hole independently, and then you can check whether those 2 independent measurements are consistent with each other and with the Kerr prediction. They were. The black hole produced by that merger was, as far as the data can tell, a perfect Kerr black hole. No hair, no memory, no deviation. Now, on one level, this is deeply satisfying. It means the theory works. General relativity, written down by Einstein in 1915, extended and refined over the following decades, continues to pass every test we put it through, even when the test involves signals from collisions of objects so extreme that the curvature of space-time near them makes words like extreme feel inadequate. But on another level, there are physicists who find the continued perfection of these measurements slightly alarming, or at least demanding of explanation. Because we know, with theoretical certainty, that general relativity cannot be the final theory. It is incompatible with quantum mechanics. At the Planck scale, roughly 10 to the negative 35 meters, the quantum structure of space-time should produce effects that classical general relativity does not account for. For a black hole, those effects should be most concentrated near the singularity and near the event horizon. And ringdown gravitational waves, which are shaped by the geometry near the horizon, should in principle carry some imprint of whatever quantum structure exists there. The fuzzball picture from string theory is one framework that predicts what this imprint might look like. In string theory, the singularity inside a black hole is not a point of infinite density. It is replaced by a tangled quantum structure, where the strings and brains of the theory are distributed throughout the region that classical relativity would describe as the interior. The event horizon, rather than being a clean mathematical surface where nothing physically special happens from the infalling observer's perspective, becomes a region of intense quantum fluctuation. Calculations suggest that this quantum structure should produce echoes in the gravitational wave signal, repeated pulses arriving after the main ringdown has faded as gravitational waves bounce back and forth between the surface of the fuzzball and the photon sphere. These echoes have not been detected. Every ringdown we have measured looks like a clean Kerr ringdown followed by noise. But the non-detection has limits. The echoes, if they exist, might be so faint or arrive at frequencies so poorly matched to detector sensitivity that we simply cannot see them yet. The overtone detection in GW 25114 was itself only possible because of the improved sensitivity of the 04 run. Phenomena that were invisible to LIGO's early runs are now beginning to appear. What might appear once the Einstein telescope, the planned next-generation European detector, comes online? The Einstein telescope is designed to be roughly 10 times more sensitive than current LIGO across a broad frequency range, and one of its explicit science goals is testing quantum gravity effects in the ringdown. With 10 times the sensitivity, the boundary of what is detectable shifts dramatically. Effects that are currently consistent with zero because our error bars are too large become measurable or demonstrably absent. That distinction between unmeasured and absent is one of the most important in all of experimental science. We are currently in the unmeasured regime for quantum gravity signatures in black hole ringdowns. The transition to the absent regime, if it comes without finding anything, will itself be a profound statement about the nature of space-time. For now, what we know is this. The black holes we are detecting are behaving like the mathematical objects general relativity predicts. The ringdown is clean, the harmonics match. The no-hair theorem holds at the precision we can currently achieve. Whether that means black holes are truly the smooth classical objects the theory describes, or whether they are quantum structures that simply have not yet revealed themselves at our measurement resolution, is one of the most important open questions in physics, and the answer is written in the gravitational waves if we can listen precisely enough to hear it. Part 5. The universe is not silent. The gravitational wave background. By the time you finish reading this sentence, the space-time around you will have been stretched and squeezed billions of times by gravitational waves from sources so numerous that they overlap into a continuous background signal, a hum that permeates the entire universe and passes through everything, including you, without depositing enough energy to be felt or measured by any instrument currently on Earth. This background exists because the universe is full of massive objects in motion, and has been for roughly 13.8 billion years, and every gravitational wave ever produced is still propagating, still stretching and compressing space, still carrying the energy of ancient collisions. In 2023, 4 separate pulsar timing array collaborations announced, within weeks of each other, that they had detected this background. Nanograv in North America, the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Indian Pulsar Timing Array. 4 independent groups using 4 separate collections of radio telescopes spread across the planet, and all 4 of them found the same signal. The probability of a coincidental detection in 4 independent datasets simultaneously is not a number worth calculating, because it is essentially zero. Pulsar timing arrays work on a principle that feels almost absurd in its elegance. Pulsars are rapidly rotating neutron stars that emit beams of radio waves from their magnetic poles. Because of the geometry, those beams sweep past Earth at extraordinarily regular intervals, some pulsars keeping time with a precision that rivals atomic clocks. If a gravitational wave passes through the region of space between Earth and a pulsar, it stretches or compresses that space by a tiny amount, which causes the pulsar's radio pulses to arrive at Earth either slightly early or slightly late. By monitoring dozens of pulsars spread across the sky and looking for correlated timing variations, you can detect a gravitational wave background passing through the entire solar system. The signal detected in 2023 looks exactly like what you would expect from a background of merging supermassive black hole binaries. Supermassive black holes, the ones that sit at the centres of galaxies and weigh millions to billions of times the mass of our Sun, are thought to merge when their host galaxies merge. Galaxy mergers are common throughout cosmic history. Every major merger event involves two supermassive black holes sinking toward the centre of the combined galaxy through a process called dynamical friction, eventually forming a binary and, over timescales of millions to hundreds of millions of years, spiralling together and merging. The gravitational waves from each such merger are not in the frequency range that LIGO can detect. They are at nanohertz frequencies, meaning one oscillation every few years, corresponding to wavelengths of light years. These are the waves that pulsar timing arrays can measure. A critical fingerprint of gravitational wave origin is the Hellings-Downs curve, which is the predicted pattern of how correlated the timing variations between different pulsar pairs should be, as a function of the angle between them on the sky. Gravitational waves produce a very specific correlation pattern because they are quadrupolar in nature, meaning they squeeze space-time in one direction while stretching it in the perpendicular direction. The 2023 detections all showed this pattern with enough statistical significance to make the gravitational wave interpretation the strong favourite. What the detection is telling us connects directly to the larger story we have been building. Every galaxy in the universe, including our own Milky Way, likely went through multiple major mergers throughout cosmic history. Each of those mergers eventually produced a supermassive black hole binary. Each of those binaries eventually spiraled together and merged, and each of those mergers sent gravitational waves radiating outward at the speed of light. Those waves are still travelling. They overlap with waves from 1 trillion other mergers across the observable universe, and together they constitute a background that is, right now, gently rocking space-time everywhere, including in the space between atoms in your body. The alternative explanations for the background are speculative but worth acknowledging. Cosmic strings are hypothetical one-dimensional topological defects that might have formed in the early universe when symmetries broke during phase transitions, similar to how cracks form in ice when water freezes. A network of cosmic strings vibrating through the universe would also produce a gravitational wave background, potentially with a slightly different spectral shape than the black hole merger background. Primordial gravitational waves from inflation, the hypothetical period of exponential expansion in the very earliest moments of the universe, represent another possibility. Distinguishing between these sources requires more data, specifically a more precise measurement of the spectral shape and angular correlation pattern of the background. But sit with the most likely interpretation for a moment. The signal detected in 2023 represents the accumulated gravitational wave output of supermassive black hole mergers stretching back billions of years. It is the universe's memory of its own violent history encoded in the space-time around us right now. Every cubic meter of space, everywhere you look, including the space inside this room, is vibrating gently with the echoes of collisions that happened before our solar system formed, before our galaxy took its current shape, before perhaps anything we would recognize as structure existed in the universe. We are not observers of a universe that occasionally produces dramatic events. We are inhabitants of a universe that is continuously vibrating with the accumulated consequences of billions of years of catastrophic collisions, and we have only just built ears sensitive enough to begin hearing it, which raises a question worth letting settle. If we can now hear the background hum of the universe's history, what else is written in space-time that we have not yet learned to read? Part 6. Black Hole. Hierarchies. The universe is building generations. There is a concept in biology called a lineage. the traceable line of descent from parent to offspring across generations. It turns out the universe may be doing something structurally similar with black holes, not through biology, but through repeated gravitational mergers in environments so crowded and so energetic that they function as factories for progressively more massive objects. And the gravitational wave catalogue is beginning to show us the product line. The story starts with first-generation black holes, the ones produced directly from stellar collapse. A massive star, something between roughly 20 and 130 solar masses, depending on its composition and metallicity, reaches the end of its nuclear fuel supply and collapses. If the collapse produces a black hole rather than a neutron star or a complete stellar disruption, that black hole carries the angular momentum of its progenitor, a spin inherited from the rotation of the star that made it. These first-generation objects are generally expected to have relatively moderate spins and masses that reflect the upper range of stellar evolution. Now put two of these first-generation black holes in a dense stellar environment. A globular cluster, for instance, is a roughly spherical collection of hundreds of thousands to millions of stars bound together by gravity, orbiting the outer regions of a galaxy. Globular clusters are old, dense, and gravitationally chaotic. Black holes formed from the cluster's most massive stars sink toward the center, through a process where gravitational interactions with other stars gradually transfer energy away from the black hole and toward lighter objects, a process called dynamical friction. Over time, many of the cluster's black holes accumulate in the core, where they interact with each other, form binaries through three-body interactions, and eventually merge. The black hole produced by that first cluster merger is a second-generation object. Its mass is roughly the sum of its parents' masses minus the fraction radiated as gravitational waves, typically around 5%. Its spin is set by the angular momentum budget of the collision, and for a wide range of initial conditions that spin tends to cluster around 0.7 in dimensionless units, a prediction that comes from numerical relativity simulations. This spin signature is one of the clues researchers use when trying to identify second-generation black holes in the data. If that second-generation black hole does not escape the cluster, it might eventually find another partner, either another first-generation black hole or perhaps another second-generation one. The resulting third-generation merger produces an object heavier still, potentially well into or beyond the pair instability mass gap. This is the hierarchical merger scenario, and it offers a natural explanation for the mass gap events in the catalogue. The forbidden zone is forbidden only for first-generation black holes. Second and higher-generation objects are not subject to the pair instability constraint, because they were not born from a single stellar collapse. What makes this more than just a theoretical story is that the simulations of dense star clusters actually produce merger rates and mass distributions that are broadly consistent with what we observe in the gravitational wave catalogue. Clusters cycle black holes through multiple generations, growing them progressively larger through a process that has been compared to a kind of gravitational alchemy, turning lighter stellar remnants into increasingly massive objects through repeated fusion events. Some simulations suggest that given enough time and the right cluster conditions, this process could produce intermediate mass black holes in the range of hundreds to thousands of solar masses, objects that represent the missing link between the stellar mass black holes detected by LIGO and the supermassive black holes at galactic centers. The mystery of how supermassive black holes got so large so fast in the early universe is one of the enduring puzzles of astrophysics. Observations show that billion solar mass black holes existed when the universe was less than 1 billion years old, which is extremely young on cosmological timescales. Growing a black hole to that mass through ordinary accretion, matter falling in and being swallowed, requires either enormously high accretion rates sustained for long periods, or a very massive seed to start with. Hierarchical mergers in the dense environments of early galaxies might have provided those massive seeds. Each generation of mergers in this picture is a step in a ladder that stretches from stellar remnants to the supermassive monsters that now anchor galaxies like our own. The gravitational waves produced by each rung of that ladder are different. First-generation mergers produce signals in the frequency range that LIGO can detect. Higher-generation mergers between increasingly massive objects produce signals at lower and lower frequencies, eventually moving into the nanohertz range where pulsar timing arrays are sensitive, and then below even that into a regime where only future space-based detectors will be able to hear them. The Laser Interferometer Space Antenna, or LISA, a planned European Space Agency mission consisting of 3 spacecraft separated by millions of kilometers forming a triangle in space, is designed to detect mergers of massive black holes in the range of 10,000 to 10 million solar masses. It will, if all goes as planned, fill in the middle range of the black hole merger spectrum, connecting the stellar mass events LIGO hears to the supermassive events that the pulsar timing arrays have now established. When all 3 of those detection windows are operating simultaneously, we will for the first time have something like a complete acoustic picture of the black hole universe. From the high-pitched chirps of stellar mass mergers detected by ground-based interferometers, through the intermediate frequencies of massive black hole coalescences detected by LISA, to the deep infrasonic hum of the gravitational wave background detected by pulsar timing arrays. The universe has been making this music for billions of years. We are building the instruments to hear all of it. Part 7. The galactic ejection problem. Rogue black holes everywhere. When 2 black holes merge, the collision is not perfectly symmetric. Even in an idealized head-on merger of 2 identical black holes with no spins, the gravitational wave emission is symmetric and the resulting black hole stays put. But real mergers involve unequal masses, unequal spins, and orbital dynamics that break every possible symmetry. The gravitational wave emission from these asymmetric mergers is also asymmetric, stronger in some directions than others. And because gravitational waves carry momentum, and momentum is conserved, the newly formed black hole must recoil. It gets a kick in the opposite direction from the strongest gravitational wave emission that can be substantial. The physics of this was worked out theoretically well before we had observational data to compare against, and the predictions are remarkable. For certain combinations of mass ratio and spin alignment, the recoil velocity can reach hundreds of kilometers per second. For the most extreme cases, involving nearly equal mass mergers with spins in particular orientations called superkick configurations, numerical relativity simulations predict recoil velocities that can exceed 5,000 kilometers per second. To put that in perspective, the escape velocity from the Milky Way galaxy, the speed you would need to achieve at the solar neighborhood to break free of the galaxy's gravitational pull entirely, is roughly 550 kilometers per second. A black hole produced with a superkick recoil would leave the galaxy in roughly the time it takes light to cross a few thousand light-years. The catalogue now contains several events that are candidates for having produced high recoil black holes. GW 20129 is one of the more studied cases, a merger with mass ratio and spin parameters that simulations suggest could have produced a significant recoil. The recoil cannot be measured directly from the gravitational wave signal with current detector sensitivity, because the effect of the kick on the waveform is subtle and requires precision beyond what we currently achieve. But the event's parameters sit in a region of mass spin space, where large kicks are theoretically expected. This leads to what researchers sometimes call the invisible population problem. Every high recoil merger event produces a black hole that may be ejected from its host cluster or even its host galaxy. These ejected black holes do not stop existing. They do not evaporate or disappear. They continue on, moving through intergalactic space at whatever velocity the kick imparted, slowly decelerating due to the gravitational drag of whatever diffuse matter they pass through, potentially over timescales of billions of years. Where do they end up? The answer is, we have no idea how to find them. A black hole moving through intergalactic space does not emit light. It does not produce any electromagnetic signal at all, unless it happens to encounter matter that falls into it and forms an accretion disk, which in the sparse environment of intergalactic space is unlikely. It cannot be seen through a telescope. It can only be detected gravitationally, either through lensing effects if it happens to pass in front of a background source, or through another merger event if it encounters another massive object, which given the scale of intergalactic distances is statistically improbable over any human-relevant timescale. What this means is that the universe may contain a significant population of black holes that are simply wandering, invisible, through the voids between galaxies. Every dense star cluster that has been running its hierarchical merger factory for billions of years has been ejecting a fraction of its merger products into the surrounding space. Every galaxy that has gone through a cluster-rich formation history has been shedding black holes into its halo and beyond. The cumulative effect integrated over cosmic history could amount to an enormous number of objects distributed through the intergalactic medium, unseen and essentially unseeable with current technology. The halo of the Milky Way, the roughly spherical region extending far beyond the visible disk of the galaxy, may contain a population of these ejected black holes that dwarfs the number of black holes remaining in the disk. Some estimates, which vary enormously depending on assumptions about cluster formation rates and merger histories, suggest that the intergalactic medium could contain more mass in wandering black holes than in the visible matter of all the galaxies combined. That is a speculative number, and the uncertainties are enormous, but even a more conservative version of the story implies a universe that is significantly more structured in its dark compact objects than our observations have so far revealed. What does this mean for the gravitational wave story? It means that the 300 events in the current catalogue represent only the tip of an iceberg. We are detecting mergers that happen in environments accessible to our current instruments, in the local universe and at moderate distances. The ejected population, wandering through voids, rarely encounters anything to merge with. The mergers they do eventually produce, if they do, happen in environments far from the dense clusters that make repeated mergers common, and potentially at distances that put them at the edge of or beyond our current detection range. The universe contains vastly more black holes than the ones currently announcing themselves to our detectors. Part 8. The mass gap might be a selection illusion. We have talked about the pair instability mass gap as a physical prediction, something that stellar evolution theory says should be empty of black holes because of what happens to massive stars before they can collapse into objects of that size. And we have talked about the events that appear to violate it, GW 19521 and others, and the hierarchical merger explanation that accommodates them within mainstream physics. But there is a third possibility that the data cannot currently rule out, and it is worth sitting with for a moment because it cuts at something foundational about how we read population statistics from gravitational wave observations. What if the gap is not real? What if it is an artifact of what our detectors can see? Detection sensitivity in gravitational wave astronomy is not uniform across mass space. The loudness of a gravitational wave signal depends on the masses involved, the distance to the source, and the orientation of the merger relative to Earth. For equal mass mergers, loudness scales roughly with the total mass of the system, but in a complicated way that depends on frequency, because the detectors have different sensitivities at different frequencies and different mass systems emit gravitational waves at different characteristic frequencies. As a general trend, more massive systems are detectable from farther away. But there is a complication. Systems in the pair instability mass gap, with individual black hole masses between roughly 65 and 120 solar masses, produce gravitational waves at frequencies somewhat lower than the most sensitive band of current LIGO-era detectors. The characteristic frequency at which a binary system's gravitational wave emission is strongest at merger is inversely proportional to the total mass. Heavier systems emit at lower frequencies. Current ground-based detectors are most sensitive between roughly 20 and a few hundred hertz. A merger of 290 solar mass black holes produces peak emission around 100 Hz or below, in a region where detector noise begins to rise. This means that the effective range for detecting mass gap mergers might be somewhat less than naive scaling would suggest. If the true merger rate of mass-gap black holes is not zero but simply reduced compared to lower mass events, and if those events are somewhat harder to detect due to the frequency mismatch with peak detector sensitivity, then the apparent gap in the observed mass distribution could be more apparent than real. The underlying astrophysical population might show a dip in that mass range, consistent with stellar physics, but not an absolute void. Events that do occur in that range might be underrepresented in our catalogue simply because a fraction of them fall below the detection threshold. This argument is strengthened by the primordial black hole hypothesis, which, as discussed earlier, would predict black holes of arbitrary mass, including the gap range. But it also applies even within purely astrophysical models. Some stellar evolution codes, particularly those that use different prescriptions for mass loss during the red supergiant phase of stellar evolution, predict that the lower edge of the pair instability gap is not at 65 solar masses, but might be as low as 45 or 50 solar masses. Other codes predict it extends to higher masses. The theoretical uncertainty in the exact boundaries of the gap is larger than the clean picture sometimes presented in overview articles would suggest. What the data can currently say is that the rate of mergers in the gap mass range is lower than at nearby masses, and that the events we do see in or near the gap have properties consistent with hierarchical or otherwise exotic formation channels. What the data cannot currently say is whether the gap is truly empty or merely underpopulated, and it cannot say with certainty whether the events we do see there require exotic physics or just the ordinary but complex physics of dense stellar environments. This matters for the central story we have been building, because it is a reminder that the gravitational wave catalogue, as impressive as it is still a young dataset being interpreted with tools that are themselves under development. The selection effects we understand are already complex. The ones we do not yet fully understand might be reshaping our picture of the black hole population in ways we will only recognize in retrospect. Science is always partly a story of learning what questions you are asking incorrectly, and the mass gap debate is a living example of that process playing out in real time. Part 9. The information paradox becomes a data problem. There is a question about black holes that has been disturbing physicists for roughly 50 years, and it has never been resolved. Stephen Hawking raised it in 1974 when he showed, using a semi-classical combination of quantum field theory and general relativity, that black holes should slowly emit thermal radiation, now called Hawking radiation, and eventually evaporate completely. The radiation is thermal, meaning it is random, carrying no information about what fell into the black hole. If the black hole evaporates and leaves behind only this random radiation, then all the information about everything that ever crossed the event horizon is simply gone from the universe, destroyed. Not hidden, not encoded in some inaccessible place, but erased. This is deeply problematic because quantum mechanics is built on the principle that information is conserved. The mathematical laws of quantum mechanics are time-reversible in principle. Given complete information about the state of a system at one moment, you can in principle reconstruct what it was doing at any earlier time. If information is destroyed by black holes, this fundamental property of quantum mechanics breaks down. Either quantum mechanics needs to be modified, or our understanding of black holes needs to be modified, or something else entirely needs to give. The tension this produces is not just philosophical. It has concrete implications for how the gravitational wave signals we measure connect to fundamental physics. Every merger event in our catalogue involves two information systems colliding and becoming one. The quantum state of black hole A and the quantum state of black hole B combine into the quantum state of black hole C. Where does the information of A and B go? In the classical general relativistic picture, it is absorbed into the interior of C, inaccessible behind the event horizon. In the Hawking radiation picture, C will eventually evaporate, and if information is truly lost, then everything about A and B is gone from the universe. Various proposed resolutions to this paradox have emerged over the decades, and they cluster around a few broad strategies. One is that information is somehow encoded in the Hawking radiation in a subtle, non-random way, and that a complete calculation of quantum gravity effects would show the radiation carrying information out of the black hole as it evaporates. This is now the mainstream view among string theorists, following insights from ADS/CFT correspondence and related developments, but demonstrating it rigorously remains an unsolved problem. Another is that information escapes through subtle correlations in the spacetime geometry itself, perhaps through what are called soft photons and soft gravitons, low-energy particles that dress the spacetime geometry and carry away information in what Hawking, Perry and Strominger proposed in 2016 as the super-translation hair of black holes. The connection to gravitational wave astronomy is indirect but real. If black holes carry quantum hair of any kind, whether the super-translation variety or something related to fuzzball structure or firewall physics, then in principle the ringdown gravitational wave signal should carry an imprint of it. The waveform might show deviations from the clean Kerr prediction at some level of precision. No such deviations have been detected. But as we have established, non-detection at our current precision is not the same as absence. There is also a more indirect way in which the information paradox intersects with the data problem we face. Even if we cannot directly measure quantum gravity effects in individual ringdown signals, the statistical distribution of events across the catalogue might carry information about quantum processes at the horizon. If information escape mechanisms operate on the timescale of black hole evaporation, which for stellar mass black holes is unimaginably long, they are irrelevant to any measurement we can make. But some proposals suggest that information processing at the horizon happens on shorter timescales, potentially leaving imprints in the gravitational wave signal that are accessible to future detectors. The honest summary is that the information paradox, despite 50 years of theoretical effort by some of the most brilliant minds in physics, remains unresolved. And the gravitational wave signals, despite being the closest observational window we have to the extreme physics of the black hole horizon, have not yet provided data that distinguishes between the competing resolution proposals. What they have done is set limits, telling us that if quantum effects exist, they are smaller than certain bounds at our current measurement precision. Those bounds are themselves scientifically meaningful, and they will tighten as detectors improve. At some point, either an anomaly will appear in the ringdown data that demands a quantum gravity explanation, or the absence of anomalies will itself become a powerful constraint on the theory space. Either outcome moves the field forward. For now, every merger we detect is both a triumph of classical general relativity and a reminder that the theory cannot be complete. The information about everything that fell into those two black holes over their entire existence is encoded somewhere in the laws of physics. Finding where, or proving that it cannot be found, remains one of the great unsolved problems of theoretical physics, and the gravitational waves these events produce are one of our best current tools for probing the edges of an answer. Part 10. Detector physics is now the limiting factor, not the universe. In the early years of gravitational wave astronomy, the limiting factor was simple and almost frustrating in its simplicity. The universe was producing events constantly. The signals were arriving at Earth on a continuous basis, and the detectors were not sensitive enough to find them. The signals were there the whole time, buried underneath the noise like a conversation happening on the other side of a wall during a thunderstorm. Every upgrade to LIGO, every improvement to mirror coatings, every new isolation system, every increase in laser power was aimed at a single goal: bring the noise floor down far enough that signals which were previously invisible became detectable. That was the problem, and crucially, it was a solvable engineering problem. Not easy, not cheap, not fast, but solvable in the way that engineering problems eventually yield to enough focused human effort and enough well-directed funding. That problem has largely been solved, at least at the current generation of detector sensitivity. The O4 observing run, which pushed through 2023 into 2025, operated at sensitivities that were essentially at or near the design goals that the advanced LIGO team had set years earlier during the planning phase. Think about what that means for a moment. Scientists and engineers wrote down on paper years in advance how sensitive they intended to make these instruments, and then they actually built them to that specification. In a field where nature constantly surprises you and technical obstacles multiply in unexpected directions, that alone is worth appreciating. The methods they use to get there are themselves worth understanding, because they reveal just how close to the fundamental limits of physics these instruments are now operating. One of the primary noise sources in modern interferometers is quantum shot noise, which arises from the discrete photon nature of the laser light bouncing between the mirrors. Light is not a smooth, continuous wave at the quantum level. It arrives in packets, in photons, and the random arrival timing of those photons introduces a fluctuation in the measured phase of the laser field that mimics the tiny displacement signal you're trying to detect. You cannot eliminate this noise by using a better laser, because it is not a property of the laser, it is a property of quantum mechanics itself. The solution that advanced LIGO and its partner detectors now employ is called quantum squeezing. The technique is borrowed from quantum optics, and it exploits the Heisenberg uncertainty principle in a somewhat counterintuitive way. The uncertainty principle says you cannot simultaneously know both the amplitude and the phase of a light field with arbitrary precision. Quantum squeezing deliberately redistributes that uncertainty, reducing it in the one quantity you care most about measuring, the phase, at the cost of increasing it in the other quantity, the amplitude, which matters less for the measurement. The result is a laser field that behaves more quietly in the relevant dimension, not because the universe became less quantum, but because you learn to negotiate with the uncertainty in a smarter way. The fact that this technique is now operational inside the world's most sensitive physics instruments, running routinely as part of standard observing runs, represents a genuine triumph of applied quantum physics. Seismic noise presents a different kind of challenge, one that's perhaps easier to visualize. The Earth is not still, it vibrates constantly, from ocean waves striking coastlines, from traffic on distant roads, from atmospheric pressure variations, from the slow grinding of tectonic plates. All of this motion couples into the ground, and from the ground it tries to couple into the mirrors of the interferometer, shaking them by amounts that are enormous compared to the gravitational wave signals being sought. The solution is a multi-stage pendulum suspension system of remarkable sophistication. The mirrors hang at the end of chains of pendulums, each stage filtering out more of the seismic noise than the last, so that by the time ground motion reaches the mirror, it has been attenuated by many orders of magnitude. These systems are now good enough to isolate the mirrors from vibrations caused by ocean waves breaking on beaches hundreds of kilometers away. The Atlantic Ocean is generating noise that LIGO in Louisiana can measure and then successfully filter out. That is the level of precision we're working at. The result of all of this engineering effort is a detector network that is now producing 100 or more candidate events per observing run. And here is the thing nobody quite anticipated when the first generation of detectors was being designed. Solving the detection problem does not end the challenges, it transforms them. The new problem is not that we cannot hear the universe, it is that we are beginning to hear too much of it to separate cleanly. The logic is straightforward once you see it. As detector sensitivity increases, the range from which events can be detected grows, because quieter signals from more distant sources become distinguishable from the noise. More range means a larger volume of the universe is being sampled. More volume means more events, and not in a linear way. The volume of a sphere scales as the cube of its radius, so doubling the detection range means sampling roughly 8 times the volume and potentially 8 times as many events. As detectors push toward greater and greater sensitivity, the rate at which events arrive at the detectors begins to climb steeply, and then steeply again. For the next generation of detectors, the Einstein telescope planned for construction in Europe and Cosmic Explorer planned for the United States, the event rate is expected to be so high that multiple merger signals will routinely overlap in time at the detectors. 2 events arriving simultaneously, or 3, or more, This is called the confusion noise problem, and it represents a genuinely new technical frontier. When two merger signals are present in the data simultaneously, separating them requires not just sensitivity, but the ability to model one signal with enough precision to subtract it cleanly from the data while extracting the other. This is a computational challenge of considerable complexity, and the difficulty scales badly as the overlap rate increases. At the most extreme projections for cosmic explorers' sensitivity, the event rate could approach 1 detection per minute. Let that number settle for a moment, because it is extraordinary. 1 gravitational wave detection per minute, continuously, from stellar mass black hole and neutron star mergers, distributed across a volume of the universe that extends to redshifts of several. At those distances, the light travel time is billions of years, meaning we would be detecting mergers that happened when the universe was a fraction of its current age, when galaxies were younger, denser, more actively forming stars and producing black holes at rates that may have dwarfed anything in the modern universe. The scientific return from such a dataset would be staggering, a nearly complete census of black hole and neutron star mergers across cosmic history. But the data analysis pipeline required to handle it at that rate does not currently exist at the necessary scale, and building it is one of the major technical challenges the field is preparing for. This is where artificial intelligence enters the gravitational wave story in a substantial and unavoidable way. Current detection pipelines already rely heavily on a technique called matched filtering, which involves taking the raw detector data and correlating it against a large bank of template waveforms, pre-computed signals covering the expected parameter space of merging systems at different masses, spins, and distances. When the data contains a real signal, it correlates strongly with the template that matches its parameters, and the event is flagged. This approach works extremely well when events are isolated in time and the template bank covers the relevant parameter space completely. For the next generation of detectors, with events overlapping and potentially unusual signal morphologies not well represented in existing template banks, matched filtering alone will not be sufficient. Machine learning approaches, particularly neural networks trained on large datasets of simulated gravitational wave signals and noise, offer complementary capabilities. They can classify candidate events, estimate source parameters, and flag anomalies in the data faster than traditional computational methods, in some cases by orders of magnitude. They can also generalize in ways that template-based methods cannot, potentially identifying unusual signals that fall outside the parameter ranges the template bank was designed to cover. The trade-off is that neural networks require careful validation to ensure they are not introducing subtle biases into the analysis, and their internal reasoning is not straightforwardly interpretable in the way that a matched filter calculation is. The deeper issue here is philosophical as much as technical, and it connects to something fundamental about how scientific knowledge is constructed. When a human scientist looks at a matched filter output and identifies a candidate event, there is a traceable chain of reasoning connecting the raw measurement to the scientific conclusion. Every step can be examined and questioned. When a deep learning classifier labels something as a binary black hole merger with certain mass and spin parameters, the reasoning is encoded in the weights of a network trained on simulations, distributed across millions of numerical parameters in a way that is not straightforwardly human-readable. This does not make the result wrong. In benchmark tests, well-designed machine learning systems perform as well as or better than traditional methods on standard events. But it does require a new kind of epistemological care in how the field assesses and validates what the data is telling us about the universe. You need to know not just that the answer is probably right, but how you would know if it were wrong. The transition from detection-limited science to signal separation-limited science is, in its own way, a remarkable story of success. The founders of this field spent decades trying to build instruments sensitive enough to hear the universe. That goal has been achieved. The problem that has replaced it, the problem of having more universe than you can currently process, is a problem that could only have arisen after the original challenge was met. We are building ears capable of hearing more of the cosmos than we have ever heard before, and learning that hearing more is only the beginning of the work. Making sense of it, separating the voices, identifying the anomalies, and letting the universe speak as clearly and honestly as it can, through whatever combination of human and artificial intelligence turns out to be necessary, is the science of the coming decades. And somewhere in that flood of signals, patient and waiting to be found, is almost certainly something that changes everything again. Part 11. AI systems are now running scientific discovery pipelines. The first gravitational wave detection in 2015 required months of careful human analysis before the team was confident enough to announce the result to the world. Hundreds of scientists spread across multiple continents combed through the data, checked for instrumental artifacts, validated the matched filter output against alternative analysis methods, ran consistency checks between the two detector sites, and documented every step of the reasoning chain with the kind of obsessive thoroughness that a discovery of this magnitude demanded. The announcement in February of 2016 came roughly 5 months after the signal arrived at the detectors in September of 2015. 5 months of checking and rechecking before anyone said the words out loud in public. That timescale reflected the extraordinary caution appropriate to a claim that would rewrite physics, and it also reflected the nature of the analysis methods available at the time, which were powerful but slow, requiring human judgment at every critical step. By 2024 and 2025, the O4 observing run was producing preliminary event alerts within minutes of detection. Not hours, not days, minutes. Those alerts were automatically distributed to astronomical observatories around the world, triggering a coordinated response where telescopes on every continent and in space were redirected toward the region of sky consistent with the merger location, searching for any flash of light or radio emission that might accompany the gravitational wave signal. This transformation, from 5 months to 5 minutes, did not happen because scientists became less careful or less rigorous. It happened because the entire analysis infrastructure was rebuilt around machine learning systems capable of processing incoming detector data, identifying candidate events, estimating the sky localization of the source, and pushing alerts out through automated channels, all in near real time, while human scientists were still sitting down with their morning coffee. This acceleration connects directly to the larger scientific project of understanding what these mergers are telling us about the universe. The speed of event detection is not just an operational convenience. It determines the scientific output of every observing run in ways that compound over time. Events missed by automated pipelines are events that never enter the catalogue. Parameters estimated incorrectly by automated systems propagate incorrect information into the population studies that drive our conclusions about the mass distribution, spin distribution, and formation channels of merging black holes. And in the case of mergers that produce electromagnetic counterparts, the speed of the alert determines whether telescopes can catch the optical or radio afterglow before it fades, which for some events happens on a timescale of hours. The AI is not a convenience layer sitting on top of the real science. It is now a fundamental component of the instrument itself, occupying the critical position in the chain that connects raw interferometer output to the scientific conclusions published in journals and debated at conferences. The classification problem that these systems are solving is genuinely difficult, in ways that are worth understanding rather than glossing over. The detectors produce continuous time series data, essentially a record of how the length of each interferometer arm is changing from moment to moment, sampled thousands of times per second. Embedded in that data stream, appearing for fractions of a second to a few seconds depending on the system's masses, are the gravitational wave signals. But the data stream also contains a continuous background of noise, and scattered throughout that noise are what the field calls glitches, transient noise events of non-Gaussian character caused by an enormous variety of sources: electronic noise in the readout systems, mechanical resonances in the suspension hardware, acoustic coupling from air conditioning systems, electromagnetic interference from nearby power lines, scattered light inside the vacuum system following unexpected paths, seismic events ranging from distant earthquakes to passing trucks. Each of these can produce a brief spike or structured transient in the data that, in the worst cases, looks disturbingly similar to a real astrophysical signal. Distinguishing a genuine gravitational wave event from a glitch requires pattern recognition across multiple dimensions simultaneously. A real signal should appear in both detectors, separated by the light travel time between them, which for the LIGO sites in Louisiana and Washington is about 10 milliseconds. A glitch typically appears in only one detector, though correlated environmental disturbances can occasionally affect both. A real signal should have a frequency evolution consistent with the inspiral of compact objects, sweeping upward in frequency as the objects approach merger. A glitch can have almost any time-frequency morphology depending on its source. Machine learning systems trained on labeled examples of glitches and real signals have proven better than traditional rule-based methods at navigating this multi-dimensional pattern space. They generalize more effectively to novel glitch types not seen in the training data, and they can operate continuously without the cognitive fatigue that inevitably affects human analysts attempting to review months of data by eye. But here is where the story becomes more complicated, and where the scientists who work in this field are most candid about the tensions involved. AI systems are trained on historical data, and they learn to recognize patterns that are present in that data. The optimization process that trains a neural network is, at its core, a sophisticated form of curve fitting, adjusting the network's internal parameters until its outputs match the desired labels on the training examples as closely as possible. This works beautifully when the events you need to classify in the future resemble the events in the training set. It becomes unreliable in ways that are difficult to predict in advance when the universe produces something genuinely outside the distribution the network was trained on. Consider what that means for gravitational wave science specifically. The training data for these classifiers consists of real detector noise with simulated gravitational wave signals injected into it. The simulated signals are generated from theoretical waveform models covering the parameter space of expected merging systems. If the universe produces a merger with an unusually extreme mass ratio, or with spin configurations that produce unusual precession effects in the waveform, or with some combination of parameters that falls in a sparsely populated corner of the training distribution, the classifier may assign it a low probability of being a real event. It might be deprioritized, missed entirely, or have its parameters estimated incorrectly. In the worst-case scenario, which is not hypothetical but is a genuine concern the field takes seriously, the AI might systematically suppress unusual events across the entire catalogue, creating a dataset that reflects the assumptions baked into the training process rather than the true diversity of what the universe is producing. This concern has a name in the field, and it is structurally related to but distinct from the natural selection effects discussed earlier in this story. Natural selection effects arise from the physics of detection, from the fact that some signals are louder than others, and some sky positions and orientations produce stronger responses in the detectors. These effects can be characterized by measuring the detector sensitivity and modeling how it varies across parameter space. AI selection effects arise from the design choices embedded in the training process, from the choice of which simulated signals to include, which noise examples to label as glitches, which parameter ranges to emphasize. These effects are harder to characterize precisely because they live inside the internal structure of a neural network, distributed across millions of numerical weights in a way that does not have a simple physical interpretation. You cannot point to a single parameter and say, this is where the bias comes from. The field is actively working on this. Validation frameworks that compare AI outputs against traditional matched filter pipelines on the same data are being developed and refined. Interpretability tools that attempt to make the internal reasoning of neural networks more transparent are an active research area. Methods for auditing AI catalogues for systematic biases by looking at the statistical properties of the detected population, are being applied to the growing event catalogue. The goal is not to remove AI from the detection and classification pipeline, which at the event rates expected from next-generation detectors would be both impractical and scientifically harmful. The goal is to understand the system's limitations well enough to correct for them when drawing population-level conclusions, just as the field has learned to correct for natural selection effects. There is a deeper philosophical dimension here that deserves at least a moment of attention, because it extends beyond gravitational wave astronomy to the broader question of how science works in an era of AI-assisted discovery. When a human scientist identifies a candidate event by examining matched filter outputs, there is a traceable chain of reasoning. Every step can be written down, examined, questioned, and revised. The conclusion is legible in a way that connects to the measurement. When a deep learning system labels an event and assigns it parameters, the reasoning is implicit in the network weights, not explicitly accessible to human inspection. The answer may be correct, and in benchmark comparisons it often is, but the path to the answer is not transparent in the same way. This matters for science because science is not just about getting correct answers, it is about understanding why the answers are correct, so that you know where the reasoning might break down, and so that anomalies can be recognized as anomalies rather than filtered out as noise. The gravitational wave project has always been fundamentally about two things: building systems sensitive enough to measure something extraordinarily faint, and then building the analytical capacity to extract genuine meaning from what is measured. The physical instruments LIGO, Virgo, CAGRA, the planned Einstein telescope and Cosmic Explorer represent one part of that system. The AI-driven analysis pipelines represent another, and the human scientists who design the pipelines, audit their outputs, interpret the catalogues, build the population models, and ask whether the conclusions make sense, represent the third and irreplaceable part. All three layers need to work together, and the connections between them need to be understood clearly enough that the conclusions at the end of the chain can honestly be traced back to the photons bouncing between mirrors at the beginning. The universe is speaking. The work of making sure we hear it accurately, without filtering its most surprising sentences through our own expectations, is the defining methodological challenge of the next decade of gravitational wave science. Part 12. Fusion energy is quietly reaching a tipping point. Far from the cosmic scale of black hole mergers, but not entirely disconnected from it, a different kind of physics milestone has been quietly accumulating momentum over the past few years. While physicists in Louisiana and Washington and Italy have been listening to the universe through gravitational wave detectors, a separate community of scientists and engineers in California, France, China, and South Korea have been attempting something that sounds almost equally audacious: recreating the interior of a star in a laboratory on Earth. Not metaphorically, not approximately. Actually compressing matter to the temperatures and pressures that exist inside stellar cores, holding it there long enough for nuclear fusion reactions to ignite, and extracting more energy from those reactions than was put in to start them. The same fundamental forces that govern what happens inside a star, the nuclear forces that bind protons and neutrons together and release energy when light nuclei fuse into heavier ones, are at the center of a decades-long engineering effort that has consumed billions of dollars, several generations of physicists, and more than a few careers staked on a promise that the physics community has been making since the 1950s. And in 2023 and 2024, that effort crossed several thresholds that the fusion community has been working toward for most of its existence. To understand why this matters, and why it belongs in a story about black holes and gravitational waves, you need to understand what fusion actually is, and why it has been so difficult to achieve on Earth. In the core of a star like our Sun, hydrogen nuclei, protons, are compressed by the weight of the star's own gravity to temperatures exceeding 15 million degrees Celsius. At those temperatures and densities, quantum tunneling allows protons to overcome their mutual electromagnetic repulsion, and get close enough for the strong nuclear force to take over, binding them together into helium nuclei and releasing energy in the process. The energy released per reaction is modest. What makes stars work is the sheer number of reactions happening simultaneously in a volume of compressed plasma larger than the entire Earth. The Sun converts roughly 600 million tons of hydrogen into helium every second, releasing the energy that makes life on our planet possible. Recreating this on Earth means solving two problems simultaneously, and they pull in opposite directions. You need to heat the fuel to temperatures that actually exceed the stellar core, because on Earth you do not have the gravitational confinement that helps stars maintain fusion at lower temperatures. Plasma hot enough to fuse hydrogen is typically around 100 million degrees Celsius, roughly 7 times hotter than the centre of the Sun. And you need to confine that plasma long enough and at sufficient density for enough fusion reactions to occur to release more energy than you put in. The plasma cannot touch the walls of any container because no material survives contact with 100 million degree matter, so you have to hold it using either magnetic fields, in the approach taken by tokamaks like ITER currently under construction in France, or by compressing it so rapidly and symmetrically that it ignites before it has time to expand, which is the approach taken by inertial confinement facilities like the National Ignition Facility. The National Ignition Facility in California achieved ignition in December of 2022. The definition of ignition that the field had settled on is the condition where the fusion reactions in the compressed fuel produce more energy than the laser energy delivered directly to the target. 192 laser beams delivering 1.9 megajoules of ultraviolet light in a pulse lasting a few nanoseconds strike a small gold cylinder called a hohlraum containing a fuel capsule roughly the size of a peppercorn. The X-rays generated inside the hohlraum compress and heat the fuel capsule from all sides simultaneously, imploding it to densities and temperatures sufficient for fusion ignition. In December of 2022, the fusion yield exceeded the laser energy delivered to the target for the first time in history. In subsequent shots through 2023 and 2024, the energy gain improved further, with some experiments achieving fusion yields several times larger than the driver energy absorbed by the fuel capsule. It is important to be precise about what this does and does not mean, because the coverage of these results has sometimes blurred a crucial distinction. The laser system at the National Ignition Facility is not an efficient machine. It consumes roughly 300 megajoules of electricity to produce the 1.9 megajoules of laser light delivered to the target, an overall wall plug efficiency of less than 1%. So even with fusion yields exceeding the laser energy delivered to the target, the facility as a whole is consuming vastly more energy than the fusion reactions produce. The ignition milestone is a physics milestone, not an engineering milestone. It demonstrates that the fuel can be made to burn, that the confinement and compression are good enough to achieve self-sustaining fusion in the laboratory. The engineering challenge of building a power plant around this physics, one where the overall energy balance is positive and the economics make sense, remains formidable and is the subject of intense ongoing work at both government laboratories and a rapidly growing number of private fusion companies. The connection to the gravitational wave story is not direct, but it is meaningful in a way that rewards careful thought. The physics of stellar interiors, specifically the nuclear reaction rates that determine how stars live, how massive they can grow before different instabilities set in, and how they die, directly controls the mass distribution of the black holes they leave behind. The pair instability mass gap discussed earlier in this story is a prediction that depends critically on nuclear physics at extreme temperatures. The photon pair production process that destabilizes massive stellar cores before they can collapse to black holes is governed by reaction rates and thermodynamic conditions that are ultimately the same kind of physics being studied in inertial confinement fusion experiments. When laboratory fusion experiments measure cross-sections and reaction rates at controlled energies and temperatures, they produce data that feeds directly into the stellar evolution codes that predict where the mass gap boundaries lie. The better we understand fusion physics in the laboratory, the better we can constrain the theoretical models that tell us what the black hole mass distribution should look like, and therefore the better we can interpret what the gravitational wave catalogue is actually showing us. There is also a parallel in the nature of the challenge that is worth dwelling on, because it speaks to something about the kind of science civilization is capable of when it commits to a long enough timescale. Both gravitational wave astronomy and fusion energy are projects that required building instruments of unprecedented precision, maintaining them against sources of noise and instability that could destroy measurement quality at any moment, and extracting meaningful signals from systems that are fundamentally operating at or near the limits of what the laws of physics permit. LIGO measures mirror displacement at the scale of 1,000th, the diameter of a proton. The National Ignition Facility must compress a fuel capsule so symmetrically that any deviation greater than a fraction of a percent results in instabilities that prevent ignition. Both projects demanded not years but decades of incremental engineering progress, each generation of scientists inheriting a more capable instrument from the previous one and passing a still more capable version to the next. And both are now in the phase where the fundamental physics milestone has been achieved, and the harder, slower, more unglamorous work of translating that milestone into reliable, scalable, societally useful capability is underway. The tokamak path to fusion, represented most ambitiously by ITER, the International Fusion Reactor under construction in southern France, is pursuing a different confinement approach, using superconducting magnets to hold the plasma in a donut-shaped magnetic bottle. ITER, when complete, will be the largest tokamak ever built, and its planned experiments are designed to produce 10 times more fusion energy than the heating power delivered to the plasma, a gain factor of 10 that would represent a decisive demonstration of the physics. Construction has faced delays and cost increases of the kind that afflict almost every large international scientific infrastructure project, but the underlying physics case remains solid, and the machine is progressing toward its first plasma experiments. Private fusion companies, a category that barely existed a decade ago, have attracted billions of dollars of investment and are pursuing a diverse range of confinement and compression approaches. Some are working on compact tokamaks using high-temperature superconducting magnets that allow smaller, cheaper machines. Others are pursuing alternative confinement geometries, magnetized target fusion, field reverse configurations, or variants of the inertial confinement approach with different driver technologies. The diversity of approaches is itself a sign of how seriously the engineering community has begun to take the fusion opportunity now that the core physics has been demonstrated. If commercial fusion power becomes a reality within the coming decades, and the engineering progress of the past few years has made that seem considerably less speculative than it did a generation ago, it will represent humanity's first successful replication of a stellar process at civilization scale. The same nuclear fire that has been burning inside stars for billions of years, the fire whose end products include the massive stellar remnants that collapse into the black holes, whose gravitational wave signatures we are now cataloguing by the hundreds, would be burning in reactors on Earth, generating electricity, powering cities, and fundamentally changing the energy economics of human civilization. There is something worth sitting with quietly in that thought, particularly in the context of everything else this story has covered. We would be listening to gravitational waves from the deaths of stars, from collisions of the objects left behind when stellar fusion fires finally exhausted their fuel, while simultaneously burning the same fusion fire that once powered those stars' cores. The universe's two most extreme and most fundamental forms of energy release, the nuclear fusion that lights stars and the gravitational collapse that ends them, connected by the same underlying physics, both finally within our reach, one to measure, one to use. That is not a small thing for a species that, in astronomical terms, has only just arrived. Part 13. Exoplanet atmospheres are becoming chemically readable worlds. Since the James Webb Space Telescope began science operations in 2022, The business of studying worlds beyond our solar system has undergone a transformation so rapid and so thorough that it has caught even the most optimistic astronomers off guard. This is a community that spent decades arguing for the telescope's construction, defending its budget overruns, and waiting through delays that stretched from the original projected launch date of 2007 all the way to the actual launch on Christmas Day of 2021. They knew what the telescope was supposed to be capable of. They had run the simulations, written the proposals, modelled the expected signal-to-noise ratios for different kinds of planetary atmospheres around different kinds of stars, and still, when the data started coming back, the quality exceeded what the models had promised. The telescope's infrared sensitivity and spectroscopic capability were designed to push atmospheric characterization of exoplanets to a new level, and it has exceeded those design expectations in ways that the community is still working through, still publishing, still arguing about in the best possible scientific sense of that word. To understand why this is significant, and why it belongs in a story about black holes and gravitational waves, and the broader transformation of how humanity reads the universe, you need to understand what atmospheric characterization of an exoplanet actually involves, and how difficult it is. An exoplanet is, from Earth's perspective, an extraordinarily faint object orbiting an extraordinarily bright one. The star outshines the planet by factors ranging from millions to billions, depending on the wavelength of light. Directly imaging the planet and studying its light is possible in some special cases, but for most of the exoplanet population it remains beyond current capabilities. What is possible for planets whose orbits happen to carry them in front of their host star as seen from Earth is a technique called transmission spectroscopy. When an exoplanet transits its star, meaning it passes across the face of the star from our line of sight, the total light we receive from the star drops slightly, by an amount proportional to the ratio of the planet's area to the star's area. For an Earth-sized planet orbiting a Sun-like star, this dimming is roughly 1 part in 10,000, a signal requiring extremely precise photometry to detect at all. But embedded in this already faint signal is an even fainter one. Some of the starlight, rather than being blocked entirely by the planet's solid body, passes through the thin shell of the planet's atmosphere at the terminator, the boundary between the day and night sides of the planet. As it passes through, different molecules in the atmosphere absorb it at different wavelengths, specific to their molecular structure. Water vapor absorbs at certain infrared wavelengths, carbon dioxide at others, methane at others still. Each molecule leaves a distinct fingerprint in the spectrum, a pattern of absorption features that is as characteristic as a barcode. By measuring the spectrum of the star during a transit and comparing it to the spectrum measured outside of transit, astronomers can extract the transmission spectrum of the atmosphere, the wavelength-dependent difference in how much light is blocked, which encodes the atmospheric composition. In principle, this technique has been understood for decades. James Webb Space Telescope did not invent it. What JWST provided was the sensitivity to make it work cleanly, reliably, and with enough spectral resolution to distinguish between molecules that have overlapping absorption features for planets that previous telescopes could only gesture at rather than characterize. The results that have come back since 2022 have been remarkable in their variety and their detail. Carbon dioxide has been detected in multiple exoplanet atmospheres, including in systems where the planet occupies what astronomers call the habitable zone, the range of orbital distances from a star where the surface temperature could allow liquid water to exist, given the right atmospheric pressure and composition. Water vapor has been detected. Methane has been detected. Sulfur dioxide has been detected in the atmosphere of a hot gas giant called WASP-39b, where photochemical reactions driven by intense stellar radiation are apparently producing it in quantities large enough to measure. Ammonia has been tentatively identified in certain spectra. Sand clouds, composed of silicate particles, have been inferred from the spectral properties of some ultra-hot giant planet atmospheres. The The sheer variety of what is being found is itself the first major scientific result, independent of any specific detection. Before JWST, the theoretical expectation was that planetary atmospheres would sort into a relatively small number of categories based on planet size, temperature, and host star type. The data coming back suggests that reality is considerably messier and more inventive than the models anticipated. Planets of similar sizes and similar orbital periods around similar stars are showing different atmospheric compositions, different cloud structures, different chemical abundances. The universe, it turns out, is not running a small number of planetary atmosphere recipes. It is running an enormous number of them simultaneously, and we're only now beginning to read them. The scientific framework being built around these observations is called comparative planetology, and it represents a genuine new discipline emerging from the JWST data. The idea is to treat the growing collection of characterized exoplanet atmospheres the way biologists treat a growing collection of organisms, not studying each one in isolation, but looking for patterns, outliers, correlations, and trends across the population that reveal the underlying processes governing how planetary atmospheres form, evolve, and are shaped by their environments. How does atmospheric composition correlate with planet mass? With orbital period? With the metallicity of the host star? With the presence or absence of other planets in the system? With the age of the system? These are questions that require not 1 or 2 or 10 atmospheric characterizations, but hundreds, and JWST is in the process of building that sample. The connection to the gravitational wave story running through this entire discussion is philosophical rather than physical, but it is real and worth making explicit. In both cases, the science is fundamentally about extracting extraordinarily faint signals from an overwhelming background of noise using precision instrumentation that took decades to build and required sustained investment across generations of scientists. A gravitational wave signal stretches the LIGO mirrors by less than 1,000th the diameter of a proton, buried in seismic noise and quantum fluctuations. A transmission spectroscopy signal changes the apparent depth of a stellar transit by parts per million across specific wavelength channels buried in photon noise and stellar variability. The detection strategies are completely different. The underlying epistemological challenge is structurally identical. How do you convince yourself and the scientific community that the tiny signal you are claiming to see is real and not an artifact of your instrument or your analysis method? Both fields have developed rigorous answers to this question. For gravitational wave astronomy, the answer involves the consistency of the signal between multiple geographically separated detectors, the match between the observed waveform and theoretical predictions, and a careful accounting of every known noise source. For exoplanet atmospheric spectroscopy, the answer involves repeated observations of the same planet in transit, comparison of different analysis methods applied to the same data, and the internal consistency of the detected absorption, features across different spectral orders and different wavelength ranges. In both cases, the community has developed a culture of skepticism and verification that is proportionate to the importance of the claims being made. The question that hangs over exoplanet atmospheric science in a way that makes it feel different from almost any other field in astronomy is the biosignature question. If life exists on a planet, it will, under most theoretical frameworks, alter the composition of that planet's atmosphere in detectable ways. On Earth, the most obvious atmospheric biosignature is the simultaneous presence of oxygen and methane, two molecules that react with each other rapidly enough that their coexistence in thermodynamic equilibrium is essentially impossible without a continuous biological source replenishing both. Other proposed biosignatures include nitrous oxide, certain phosphine signatures under specific conditions, and the specific ratio of oxygen isotopes in atmospheric carbon dioxide. JWST cannot directly detect oxygen in transmission spectroscopy for Earth-sized planets around Sun-like stars, because oxygen's absorption features in the relevant wavelength range are too weak relative to the noise floor, but it can detect methane, carbon dioxide and water simultaneously, and the combination of these in certain ratios in a habitable zone, planet's atmosphere would be at minimum a deeply interesting data point. The community approaches this question with a level of caution that is worth respecting rather than finding frustrating. The history of claimed biosignatures is not a clean one. The announcement in 2020 of a phosphine detection in Venus's atmosphere, interpreted by some as a potential biosignature, did not survive subsequent scrutiny and reanalysis of the data. Dimethyl sulfide, a molecule produced by marine microorganisms on Earth, was tentatively reported in the atmosphere of an exoplanet called K218b in 2023, and the claim remains contested and under investigation. Non-biological chemistry is creative and complex, and the universe has had billions of years to produce interesting molecular combinations through purely geological and photochemical processes. The bar for claiming biological origin of any atmospheric feature is correspondingly high, and the community has been careful not to clear it prematurely. What is new, and what JWST has genuinely delivered, is the capability to ask the question with real data from real planetary atmospheres rather than purely theoretical speculation. A decade ago, exoplanet science was largely a census project. We were counting planets, measuring their sizes, estimating their masses, mapping their orbital architectures. It was important science, but it was astronomy at arm's length. Now, we're doing chemistry. We're reading the molecular composition of skies on worlds orbiting other stars, detecting the products of atmospheric chemistry driven by alien sunlight, mapping the diversity of planetary environments across a sample that grows with every new set of observations. The universe turns out to be full of planets with atmospheres, and those atmospheres are full of information. We have just built the instrument capable of reading it, and we're only a few years into what will almost certainly be decades of discovery. Part 14. Earth's climate system is entering extreme variability regimes. The gravitational wave story at its core is a story about detecting and interpreting signals from systems operating at the edge of physical extremes. It turns out that Earth's climate system, the coupled ocean-atmosphere cryosphere machine that has maintained conditions hospitable to complex life for hundreds of millions of years, is itself being pushed toward operational regimes that share a structural similarity with those physical extremes. High sensitivity to initial conditions, non-linear feedback loops, rapid state transitions, and outcomes that are difficult to predict, precisely even when the direction of change is clear. The past several years have provided data points that climate scientists describe using language borrowed from dynamical systems theory. 2023 was the warmest year on record, by a margin large enough to surprise even researchers who study temperature trends as a profession. 2024 approached or exceeded that record. Sea surface temperatures in the North Atlantic reached anomalies in 2023 that were so large relative to the historical distribution that some researchers describe them as statistically almost implausible, given the historical variance of the system. The El Niño event that developed in 2023 was not unusual in itself, but its interaction with the underlying warming trend produced regional extremes in temperature and precipitation that were. Complex dynamical systems, whether they are binary black hole systems spiraling toward merger, or climate systems being driven by increasing greenhouse gas concentrations, share a feature that makes prediction difficult. Sensitive dependence on initial conditions combined with positive feedback loops can produce rapid transitions to qualitatively different states. In black hole physics, the transition from in-spiral to merger is a one-way door, a point of no return after which the final state is determined by the mass and spin alone. In climate systems, the analogous thresholds, points beyond which feedbacks become self-sustaining regardless of external forcing, are called tipping points, and they are the subject of intense current research. The scientific community's understanding of these tipping points and their interactions has grown considerably more sophisticated in the past decade. Individual potential tipping elements include the Greenland and West Antarctic ice sheets, the Amazon rainforest, and permafrost systems in high northern latitudes. Each of these has threshold behaviours where changes beyond a certain magnitude could be self-sustaining. Whether any of them have been crossed or are approaching their thresholds is a question being actively investigated with improved observational and modelling capabilities. The epistemological position the field occupies is worth noting. There is strong scientific consensus on the direction of climate change and its primary cause, the accumulation of greenhouse gases from human activity. The areas of active scientific debate concern the precise timing and magnitude of specific consequences, the locations and values of tipping thresholds, and the regional distribution of effects. The uncertainty in these details does not create uncertainty about the overall direction, just as uncertainty in the precise mass and spin parameters of a detected black hole merger does not create uncertainty about whether a merger happened. Part 15. Quantum computing crosses the error threshold debate again. At the same time that gravitational wave detectors were pushing toward their quantum noise limits and extracting the finest details ever recorded from a black hole merger, a different community of physicists was grappling with quantum mechanics from the opposite direction. Not trying to measure the quantum effects that appear in physical systems, but trying to build artificial systems that compute using quantum mechanical principles. The fundamental challenge in quantum computing is decoherence, the tendency of quantum systems to lose their quantum properties through interaction with their environment. A qubit, the basic unit of quantum computation, must maintain a superposition of states, the quantum mechanical condition where it is effectively in multiple states simultaneously, long enough to perform useful calculations. Noise from the environment constantly perturbs qubits, collapsing their quantum states into classical ones and introducing errors. Error correction is possible in principle, using redundancy to protect quantum information the way classical computers use checksums to protect digital data. But quantum error correction is dramatically more resource-intensive than classical error correction. In 2023 and 2024, Google, IBM, Microsoft, and several other organizations announced results that they described as steps toward fault-tolerant quantum computation. Microsoft in particular reported achieving what they described as a topological qubit, with significantly reduced error rates using a novel physical implementation based on Majorana fermions, a type of exotic quasi-particle that some physicists had been proposing as a route to inherently more stable qubits for decades. The experimental claims were met with the mixture of excitement and skepticism that such announcements reliably generate in the field. The connection to the gravitational wave story and to the physics of black holes is through quantum simulation. One of the most compelling potential applications of quantum computers is simulating quantum systems that are too complex for classical computers to handle. The quantum many-body problem, where you're trying to compute the behavior of a system with many interacting quantum particles, grows exponentially hard for classical computers as the system size increases. A quantum computer could in principle simulate such systems efficiently, because it is itself a quantum system and can naturally represent quantum states. Black hole interiors, if they are described by quantum gravity theories rather than the classical general relativity that breaks down at the singularity, are quantum many-body systems. The fuzzball picture, the firewall proposals, the quantum information theoretic approaches to the information paradox, all of them involve quantum dynamics at scales where classical simulation is impossible. A sufficiently powerful and reliable quantum computer could simulate these systems and test whether they produce the kind of gravitational wave signatures that would be visible to next-generation detectors. This is not a near-term prospect. The gap between current quantum hardware and the computational power needed to simulate black hole interiors in any physically meaningful way is enormous. But the direction of progress in quantum computing, from laboratory curiosities to systems capable of sustaining quantum coherence long enough to perform meaningful computations, mirrors in some ways the direction of progress in gravitational wave astronomy, from theoretical prediction to first detection to routine precision science. The philosophical underpinning of both projects is similar. We are trying to probe nature at its most fundamental level, where the rules that govern ordinary experience break down, and more fundamental structures become visible. Gravitational wave astronomy probes the extreme curvature of space-time near merging black holes. Quantum computing probes the quantum structure of information and computation. Both fields are now producing results that their founders would have considered remarkable, and both are pointing from different directions toward the same region of physics, the place where quantum mechanics and gravity meet, where the smooth space-time of general relativity and the probabilistic structure of quantum mechanics must somehow be reconciled into a single consistent theory. We can now hear the universe. We can hear it chirping and ringing as black holes collide billions of light years away. We can hear the deep cosmic hum of a billion supermassive black hole mergers overlapping into a background that fills all of space. We can read the chemical signatures of alien atmospheres. We are learning to harness the same nuclear fire that powers the stars. We are building machines that compute by manipulating the quantum states of matter. Each of these is a separate front in the same campaign, the human project of understanding what the universe actually is at its deepest level, rather than merely what it appears to be from our brief vantage point on a small planet in an ordinary galaxy. The black holes we have been listening to for 10 years are not just astrophysical objects. They are the universe's most extreme experiments in the physics of space-time, mass, information, and quantum gravity. They ring like bells when they collide, and the tones they produce carry information about the geometry of space-time at scales we cannot visit, in regimes we cannot replicate in any laboratory. Every gravitational wave event in the catalogue is a free experiment run by the universe itself, with parameters and energies that dwarf anything human technology can produce, and our job is simply to listen carefully enough to understand what the results are saying. We have been listening for 10 years, we have heard more than 300 events, and if the history of this field is any guide, the most important thing we will learn from gravitational waves has not yet arrived at our detectors. It is out there right now, travelling toward us at the speed of light, carrying information about something that happened in the universe, at a time and place we cannot imagine, and it will arrive, rippling through the earth and through everything on it, waiting for an instrument sensitive enough to notice. What it tells us when it does might be the most important sentence the universe has ever spoken.